Good day to all of you. Welcome to this webinar on Huygens and on low signal data. My name is Vincent Schoonderwoerd and I'm one of the imaging specialists at SVI. Today I will give a 20-minute overview of how to optimally use Huygens for low signal data. During this webinar, you can already submit questions using the question form on the right-hand side of your webinar page. At the end of the webinar, we will try to answer the questions that were submitted. If there is not sufficient time to answer your questions, we will get back to you via email. We all use microscopes to image the objects that are in fact too small to be seen with our naked eye. Yet what we need to realize is that the microscopy image is just a representation of the object. Objects are degraded by background signal and blur due to the diffraction limit of the optics, and also noise is added during the imaging process. There are even many more imaging problems that can be introduced, such as drift, bleaching, and chromatic aberration. We can correct for all these with the Huygens tools, but we focus in this webinar on background blur and noise. Let's now consider an example where we have three colored objects. Background signal caused by, for example, scattered light and background staining contribute to the total signal of these objects. A signal comparison between these objects can give you a specific ratio. This ratio completely changes when more background is included during the acquisition. So it is imperative that the background signal is corrected before you are performing any type of quantification. This also means that with very low photon counts, the contribution of noise to the image buildup becomes significant and will hamper object recognition in raw data. Luckily, with the help of deconvolution algorithms and the point spread function, we can better distinguish real signal from noise. Key to determining the background, the correct background setting, key to this is determining the correct background setting. A too high setting will remove noise, but also real signal. Photon noise is more significant with low signal as it follows a square root relationship with the signal. So with more photons, noise becomes less of a problem. You can also see that in the right cartoon, where with every image from the left to right and top to bottom, the number of photons per pixel increases tenfold. So I made a slight mistake. This also means that with very low photon counts, the contribution of noise to the image buildup becomes significant and will hamper object recognition in the raw data. So luckily, with the help of advanced deconvolution algorithms and the point spread function, we can better distinguish real signal from noise. Key to this is determining the correct background setting. So if this is too high, we will remove noise, but we will also remove signal, and that will hamper the recognition of the real data. In Huygens, we have a sophisticated approach for determining the background value. This can be explained with the following simple schematic. The complete image is convoluted with a Gaussian filter to remove any isolated high pixel values. After this, Huygens will look for a region with a fixed radius, so a sphere, with a fixed radius with the lowest value. This region is filtered with another Gaussian filter from which the background value is derived. The background value is critical in determining what pixel value is considered background and what is part of the PSF of the object. Within the Huygens software, there are different background estimation modes. For confocal data, we offer the option lowest and in-near object. Lowest takes the lowest value, whereas in-near object looks for the sphere within or close to a region of high intensity. The wide field setting is specifically offered for wide field images and looks in regions where the object is in focus. We have, in close collaboration with Professor Ben Glick and Dr. Casey Day from the University of Chicago, regarding their samples with extreme low signal, found some interesting things. They are interested in tracking secretory compartments in yeast cells. With their acquired confocal data, most pixels have a value of 0 or 1, as you can see in a single plane displayed in false colors. Also in the histogram, you can see the pixel distribution. Rarely you find pixel values with a value higher than 5. Pixel values have on average a value of 0.0104, which indicates how sparse the signal is. Ben and Casey found that some objects are not restored properly, but that the pre-filtering step before deconvolution preserves their objects. Such a pre-filtering step is a risk because it can also generate objects from noise. In response, we further fine-tuned our background estimation in Huygens specifically for such extreme low photon levels. So then we talk about photon pixel values of 1 or 2. Deconvolution with different manually set background values to 0.05 and 0.01 shows the effect of a slight adjustment in background value. So you can see that some objects can be rescued. Luckily, the automatic estimation mode in Huygens is very accurate and restores, with using the classical maximum likelihood estimation algorithm, all objects without generating any artifacts. So the automatic background estimation mode calculated the background value on this image of 0.000057, which is obviously extremely low. Most deconvolution algorithms are not suited for dealing with both high and low signal images. Although the Richardson-Lucy, displayed here, can deal with noise, Poisson noise, its limitation is that it cannot be regularized. That can be done with the blind deconvolution algorithms or the algorithms based on a maximum likelihood estimation. The MLE algorithms can be found throughout our software products. And we have several maximum likelihood estimation algorithms available in our Huygens software. One of them is the CMLE, it's the classical one. This is very robust and widely applicable for all types of images. You have lots of experience with that, and it's proven its value. QMLE is fast, suited for very compute-intensive situations, but it only works best on high signal data, and that's often wide field data. GMLE, which is the good roughness MLE, has been shown to be very good for very noisy data like stat or confocal. It's much faster than the CMLE, but relatively new, and it is more stricter in terms of sampling of data. So the quality of the data needs to be really good. As mentioned, the deconvolution algorithms can only deal with both high and low signal images if they include a regularization parameter, which in Huygens is specified as a signal-to-noise ratio. It is present within the last step of the deconvolution wizard. The SNR can be adjusted to get the best possible result out of your raw data. The Huygens Deconvolution wizard helps the user by offering default values that are set according to the microscope type that is being used. So if you have confocal, you are presented a value of 20. If you have wide field, 40. And if you have stat images, this is 7. By adjusting this SNR, you can push the resolution and signal and get rid of the noise in the data. With higher SNR values, the more frequencies will be obtained and the result becomes sharper. In this specific stat 3D image of a dinoflagellate, and then we want to thank Elisa Berdalet and Timo Zimmerman from the Center of Genomic Regulation in Barcelona for this great image. You can see in the MIP rendered data, raw and deconvolved, and in the single slice, the improvement after deconvolution. With increased SNR values, you are able to increase the signal and resolution. The line profile here shows that with different SNR values, the signal can improve up to 3 times and resolution to 1.5 times in XY. But like with image acquisition, you need to be aware of artifacts. A too low signal to noise ratio, for example, will still give a too smooth result. A too high signal to noise ratio setting can give you noise enhancement. And for this, I'm presenting here the noisy data from Convocal from Jennifer Watson and Eva Weigel. And here we've deconvolved with different SNR settings, and you see that at a value of 20, you are creating noise in the background of the data set. So it's better to deconvolve this a value of 5 or 10. Another example, and this is high signal data from a delta vision microscope, which is a wide field microscope, shows ringing. Ringing might become apparent around high intensity regions. When using a signal to noise ratio of 100, this ringing is apparent as dark halos around these high intensity objects. And with a signal to noise ratio of 40, it's a much better match and still gives a lot of improvement and signal and resolution gain from your raw data. So back to the power of SNR regularization. What is better than to show that on the same sample? So a sample that has been imaged under low laser intensity conditions and high laser intensity conditions. So this was a confocal data set from a Zeiss OSM 510 from Pavel Pasierbek. If we deconvolve both images with the SNR that matches to these specific images, we can obtain results that look very similar. Also, this paramecium example from Anne Aubusson, imaged on a Leica system, shows that with different line averaging, so different noise levels in the raw data, and using different SNR settings in Huygens, you can get almost similar results. We need to make an important remark here, and that the image should not suffer from any clipping at the low and high intensity values. Also, and we show that on the same paramecium sample, undersampling is not what should be done. So on the left panel here, we see undersampled data, 779 by 299 nanometers in X, Y, and in Z. This is undersampled, here is properly sampled, and this is slightly oversampled. And we see that with undersampling, we are losing objects. Thus, the sampling interval should be optimal. The optimal sampling interval can be calculated with the help of our Nyquist calculators that you can find online or in the Google App Store. We would like to add to this advice that you need to keep the sampling as a priority and accept lower signal in your data. And we've seen throughout this webinar that Huygens can cope with these extreme low signal levels. I would like to finish with the remark that optimal deconvolution does not remove objects, like for example filtering can do. Here is an example of a dendritic tree that after background subtraction and filtering shows a smoothing of the objects. Deconvolution on the other hand, which is on the complete right side, gives a boost in signal, but it also may suggest a removal of the objects, as can be seen in this interrupted dendrite. Please remember that the purpose of deconvolution is to correct the out of focus signal and to reassign it to the correct object location. And this can be nicely seen in the 3D volume rendered versions of this image. So this was just a single slice. Here are the 3D volumes, and you see that this dendrite is not interrupted. It's continuous, but it's just going through adjacent planes. And here, what is also nicely seen is that you're losing objects with filtering, with smoothing the signal. So this is not a good idea. The increase in signal intensity after deconvolution can also result in that some objects seem dimmer. Thus it is important to inspect the 3D volume and to look at the 3D volume and to all the objects and to adjust the gamma and brightness to confirm the presence of the objects. We've now reached the end of this webinar. I want to thank you for your attention, and I would like to offer you the opportunity to send us questions. We can deal with them later on. We just pick out a few here. So let me start with the first question. Is oversampling of data needed, or will that improve my data? Well, the answer is not, because a microscope has a limited bandwidth. It can only record a limited level of high frequencies, and at a certain point it stops. So oversampling will not improve the acquisition of higher frequencies even beyond that bandwidth. Then the second question is, which parameters can I further use to optimize my deconvolution result? Well, in the last step of the deconvolution wizard, you can also increase the amount of iterations, and you can decrease the quality threshold, which is the difference between two subsequent rounds of iterations. And if you do that, you continue with deconvolution and you have a chance that you will further improve the result. And then a second question to that is, what if I then still cannot get good results? Well, then we advise you to very thoroughly inspect the image. In fact, you should do that every time and look for additional artifacts. We've seen many times in images that improvements cannot be obtained correctly because there is, for example, stage drift in the sample. If you're still doubting about the results, just contact us, ask us questions, send us the dataset, and we will be happy to have a look at it. I want to thank you for your time, and we will get back to you via email with answers to other questions.